Hi, my name is Andrew Shin, and this is Kuniaki Saito, and we're from Machine Intelligence Laboratory at the University of Tokyo. It's an honor to be standing here. We thank you for the GPU, and we're going to be talking about our strategy on the VQA challenge on abstract scenes. First, we're going to talk about our approach that won the challenge itself, and then after the challenge was over, we were able to further improve on the results by a pretty big margin using a somewhat different approach. So we're also going to talk about it in the later part of the presentation. So starting with the approach that won the challenge, as opposed to the attribute-based features as described in the baseline paper, we have deep holistic features of two kinds. One is the uppermost convolutional layer from ResNet with 152 layers, and the second one is the FC7 layer from VGG with 19 layers. Well, these are pretty generic ways of extracting features from the images, so there's nothing really special about it. But then we also have two ways of extracting region features. One is the average softmax on top regions, and the second one is bullet coding on region proposals. But then we only apply one of these at a time, depending on the type of question, which is determined by Q-phase extraction. So starting with the first region feature, which is the average softmax. We extract top 10 regions based on the object-based measure using the proposal. And then we extract 201-dimensional softmax probabilities using FastRCN and VGG, which is trained on the ILS-BRC object detection task on 201 classes. And then we simply average out the vectors over 10 regions. So, the basic idea behind this is that there's only a few visually conspicuous objects in the image, so that it will probably suffice if we could account for those visually conspicuous objects in the image. And the second approach for region feature is the bullet coding. First, we run selective search on the image, which returns hundreds of region proposals per image. And then, again, using FastRCN, we extract the CNN features from each region proposal, and then we PCA to 256-dimensional vector. And then we concatenate 8-dimensional coordinate vector consisting of the minimum maximum center for x and y, and then width and height. So we now have two 64-dimensional vector for each region proposal, and then we apply graded coding with one cluster. So we end up having two 64-dimensional vector per image. And the motivation is kind of the opposite of the average softmax, which is to account for every possible region in the image, and then kind of generalize over all of them, so that we end up having kind of the overall general characteristic of the image. Well, so in the baseline method, they have the holistic features for the image features, and then the question features, which are generated using the LSTM, and then the image features and the question features are then aggregated onto the common embedding space, which then performs the classification of the answer. And now we're kind of augmenting the space for the image feature to include two kinds of deep holistic features and either one of the region features depending on the question. And the rest of it is pretty much identical. But then we alternate between average softmax and bullet coding depending on the type of questions. It turned out that average softmax work better on yes or no questions and number questions, and bullet coding work better on the others category. So, for example, if the question contains phrases like how many or what is the number of blah blah blah, then it's obviously a number question. So we apply softmax instead of bullet coding, and so forth for other categories. categories. Using this approach, we were able to outperform the baseline by approximately 2 points on average in both categories. And after the challenge was over, we were able to further improve the results and outperform our own score using a slightly different approach. So Saito here is going to talk about it.
Okay, my name is Kuniaki Saito, and I would like to introduce our further improvement method. So we implemented some ideas of network on visual question answering and achieved further improvement compared to the result of the challenge. So we call this our proposed network DualNet. And the key point in our idea in this visual question assign network is structure to fuse various features. So in visual question assign, we have to fuse the image features and sentence features in some steps. So there are many options to fuse the image features and sentence features, like the multiplication or summation. And at this point, we thought that the information flow extracted from multiplication and the information from summation should be different. So we think about performing both multiplication and summation in the network. Our proposed network architecture is on this slide. We used holistic feature and feature from ResNet as image features and generate sentence feature as by LSTM. And first, we projected the image feature into image feature and sentence feature into common space. We prepared two kinds of common space. The first one is common space for the multiplication, and second one is for summation. And in the second step, we conducted element-wise multiplication and summation. And finally, we concatenated the image feature from multiplication and summation. So on this slide, the red block means the feature from multiplication, and the blue block means the feature from summation. So we concatenated these features and input them to the fully connected layers. We conducted some model ensembles. We prepared 4 models with different common space dimensions. So we changed the dimension of the projected common space differently and assembled 4 models result. And we could improve our scores significantly compared to the result on the challenge. So on the unpredicted task, we could improve our score by 2.3%. And on the multiple choice task, we could improve our score by 2.9%. So I will make a summary on our presentation, and we presented the method we used in the challenge. We used holistic features and deep holistic features and region features. We used region features to extract more local features, and we wanted in this challenge. And furthermore, I introduced the improved method after this challenge. We performed reconstruct the network which perform both multiplication and summation in its network. So our work was funded by Impact Program of Council for Science, Technology and Innovation. So we published a paper about the method of our on this challenge and further improvement result. So if you are interested in our research, please see this paper for more detail. That's all for presentation. Thank you for listening.
Thanks, Andrew and Kuniaki. we can take a couple of questions from the audience. Congratulations. And I was curious if you did any analysis about the influence of the images versus the text.
I think the workshop itself reports the results on question alone. Actually, like there's nothing really novel about the text part in our approach. So yeah, it's mostly dealing with the image features. So yes. So,
Does anyone else have any question?
Hi, have you had time to try your architecture on the real images also? Did you have time?
we did. We actually placed we actually were sixth place in the real images category, I think.
Oh, it's on the leaderboard?
Yeah.
Okay, so thank you.
And yeah.
So I was surprised to see that you were able to make ResNet and VGGNet all trained on real images work on these clip art images.
Sorry.
So your approach used ResNet but trained on real images, and you used it for clip art images and
okay.
abstract scenes. Right? I didn't see a line in there where you said you retrained it or anything. You just took it.
Yeah, we didn't fine tune anything, but then using ResNet or VGG alone results in like 60, I think like 2 or 3, like lower than the baseline. So
right.
That alone doesn't really work. So yeah.
Okay, let's thank the speakers again.